right, line A5, learning task number 4. This is the third video as we go through our balanced three-phase circuits. And right now we're going to go and take a look at what we would refer to as our delta to delta type of calculations over here. Because we're working strictly with delta, we only have to worry about the delta type of specialized configurations. Don't worry about that. That's just my cat working up a hairball in the background. The delta configurations, we know that for a delta, I line is equal to my I phase multiplied by root 3. And we know that for a delta as well, my E line is equal to my E phase. Those were our two specialized formulas that we had to deal with whenever we were dealing with delta types of circuits over here. So let's go and apply them into these ones over here. We're going to go and follow through that exact same thing that we've been doing before. We are going to go and use our source to go and figure out our volts. Once we know what our volts are, we are then going to take them down to our load. Once we know what our volts are over top of the load, we can figure out our amps. And then once again, once we've got our volts and our amps together, we're going to go and figure out VA, which we are then going to go and multiply by power factor in order to go and get us to our watts that we are going to go and have. All right, let's go and step through that. First thing we're going to do is we're going to identify the information that we have. We've got 120 volts as each of my phase values of voltage. I see that I've got resistances of 10 ohms for each of my phase resistances. Note that this is different than the previous two calculations. The previous two calculations had impedances of 10 ohms that had a power factor. These are resistors. Therefore, as resistors, they are going to go and have pure 100% power factor off of them. So we don't need to worry about using any sort of a power factor. It's just going to be watts and VA will be equivalent. Beautiful. Makes our life much easier. First thing we're going to do is we're going to figure out our line value of voltage that we are going to go and have. So E line is equal to E phase. Well, that's really easy because E phase is equal to 120 volts. Therefore, my E line is going to be equal to 120 volts line. The next thing that we have to figure out is we have to figure out our current at the load. Current at the load is going to be found by finding our phase value of voltage and our phase value of resistance. This is a phase value that we have over here. Draw that as a P. So we need to go and have our phase value of voltage as well. Well, we know that E line is equal to EP, so if I've got 120 volts line, therefore I'm going to go and have a phase value of 120 volts as well. Now that we have two phase values, we can go and use Ohm's law. Ohm's law states that I is equal to E divided by R, and we're going to make sure these are all going to go and be phase values over here. My phase value of voltage is 120 volts, so we'll place that in there, 120 volts. My phase value of resistance is 10 ohms. We'll go and place that inside there. And therefore, my current, 120 divided by 10, is going to go and give me a value of 12 amperes. 12 amperes is going to become my I phase. I phase is equal to 12 amps. Perfect. The only problem is that that phase value of current is also going to get added to another phase value of current that's also going to be 12 amps. They're going to enter this node, and then both of those together are going to form one supercurrent that is going to head out on our line. We're going to go and call that thing the line value of current. So we need to go and use our delta configurations to go and calculate this. We know that I line is equal to I phase times root 3 for a delta type of system. I phase we already have, it's 12 amps, so we're just going to drop that one right into there. 12 times root 3, and that's going to give us our line value of current. 12 times root 3 equals 20.78. So 20.8 amps is what we are going to go and have over here. All right, so now we have got I line equals 20.8 amps. Write that in here, 20.8 amps. The next thing that we're going to look for is going to go and be our VA. And VA is found by me taking my E line multiplied by my I line multiplied by root 3. We've got values of line voltage, 120 volts. We've got values of line current, 20.8. And we have root 3 as a constant, so we can just go and place these into here. 20.8. 120 volts over here. 120 times 20.8 times root 3 is going to give us our VA. Let's go back to our calculator. 120 multiplied by 20.8 multiplied by root 3 gives us a value of 4,323 VA that we are going to go and have. So we'll drop that value in over here. 4,323 VA is our total amount of VA that we have out of this thing. Because we've got all resistive loads over here, that means that our power factor is 1.00 or 100% that we are going to go and have, which means that when it comes to my watts, watts are equal to my VA times my power factor. So we're going to go and take my VA, multiply it by a power factor of 1.0. 4323 multiplied by 1.00, which gives me watts that are going to be equal to my VA. Say that 4,323 is my watts and it's also my VA. You could write these as kilowatts, you could write these as kVA, or you can write them as straight watts or straight VA. It doesn't matter which one you want to go and deal with. Okay.